Next up, we're going to do some examples that help us understand the convolution property. So this is going to be 4.4.3. And real quick, I'm going to write again that definition of convolution is f star g of t is equal to the integral of 0 to t f of tau g of t minus tau with respect to tau. And the reason we're going to do this example working with this definition is because convolution can come up quite a bit in these Laplace transform problems. So you need to be able to understand how to compute a convolution. And for this example, we're looking for the convolution between e to the t and sine of t. And so that's going to be the integral from 0 to t of e to the tau sine of t minus tau integrated with respect to tau. Having a minor screen issue, sorry. There we go, that should be working now. So I'm just going to go ahead and tell you that if I integrated this, I would get that it's 1/2 e to the tau sine of t minus tau plus e to the tau cosine of t minus tau. That's just computing this integral right here. And we want to evaluate that from 0 to t. And remember that we integrated with respect to tau. So the t is replacing all of our taus right there. So that's going to give us 1/2 all times e to the t sine of t minus t plus e to the t cosine of t minus t minus e to the 0 sine of t minus 0 minus e to the 0 cosine of t minus 0. Or 1/2 times e to the t sine 0 plus e to the t cosine 0 minus e to the 0 sine t minus e to the 0 cosine t. And then since we know that sine of 0 equals 1, sine of 0 equals 0, cosine of 0 equals 1, and e to the 0 equals 1, this is just going to give us 1/2 times e to the t times 0 plus e to the t times 1 minus 1 times sine t minus 1 times cosine t. So that's just 1/2 e to the t minus sine t minus cosine t. That's the convolution between e to the t and sine t. So a quick self-check to make sure that you've done a convolution properly is to make sure that there are no taus after the convolution. We introduce taus in this integral definition of the convolution, but we integrate with respect to tau, so if you still have taus left over at the end, something went wrong. Just that can be a pretty easy mistake to make in this section. So then real quick, let's see how we use this property. So remember that we said that the convolution property is that L of f star g is equal to f of s times g of s. So the forward direction would be if we wanted to compute L of e to the t star sine t, which we just learned is just, I'll give myself like 2 spaces for that, 1/2 times e to the t minus cosine t minus sine t, I think. Yep. So supposing that we wanted to compute L of e to the t star sine t, or this function, we know from the property that this is going to be f of s times g of s. So it's going to be L of e to the t times L of sine t. And so we could just use our table of Laplace transforms to know that L of e to the t is 1 over s minus 1, and L of sine t is just s squared plus 1 in the denominator and 1 on top for our k. So that L of 1/2 e to the t minus cosine t minus sine t would just be 1 over s minus 1 times s squared plus 1. But in general, like that computation right there isn't really helpful to be doing. So don't compute f star g and then plug it in to compute the Laplace transform. Really what we're interested in here is the product property. Go right to product property. Okay, so that's just because we did this example showing how to compute a convolution, but when you're actually interested in what the Laplace transform is, that convolution didn't matter. So even though we did that right here, I'm telling you, don't do that. It comes up later in the problem when you're solving a differential equation. Don't do it right here. Also, I will say this here. I defined convolution like at the start of the lecture videos right here, and then I defined it right here when we did this example, and I've used the star symbol to denote convolution, and I'm going to tell you that star symbol doesn't mean multiplication. Somebody's going to treat it like multiplication anyhow. Please don't do that. If you treat it like multiplication inside your Laplace transform, it actually makes your job quite difficult. It's convolution, it's something different, and it means that strange integral property, which most of the time you don't even need to know. You just need to know that it's not multiplication. Okay, so I'm going to do an example in the next video where we do the inverse of the convolution property, and that's when the definition of the convolution actually comes back into play.